Today we will talk about stress and strain. Suppose that you have a body, an object, for instance a balloon that looks like this. Even if my balloon does not look like a balloon, but bear it. Alright? If you exert an empty bucket on the balloon, this is the original balloon. This is the case where you have exerted an empty bucket on the balloon. Now, what will happen to this balloon is that the internal molecules of the balloon, they will rearrange themselves in order to form a flattened surface, in order to form a flattened balloon. The same thing happens if you have a wire. If you pull the wire in both ends, if you pull the wire at both ends, the wire will be elongated. That is, the molecules, the internal molecules of the original wire rearranges themselves in order to fit in the new dimension that you have just caused by your force. As a result, a body is said to be in a state of stress when it is being distorted by an external force, and this force causes the atoms of this body to be displaced from their equilibrium position. What you have just done to this balloon and this wire is that you have just exerted stress on the materials. That is, you have just put them in a state of stress. Stress can also be defined as the force per unit cross-sectional area over which the force acts. The SI unit of stress is Newton per meter squared or Pascal. Newton per meter squared or Pascal. The British system commonly uses pounds per square inch. There are three classes of stress that we'll consider. The first one is the tension, the other one is the compression, and the third one is the shear. Now suppose that we have a book on a table that looks like this. Okay, this is a book. It's on a table. Alright. And on this table, we assume that this book is without stress. Now, suppose that you exert tension on this book. We are considering the three classes of stress, which are the tension, the other one is the compression, then the shear. If you exert tension on this book, it will look like this. It will be expanded. The book will be expanded. Let's assume that the dotted lines represent the original shape of the book. Then the new length, the new dimension of the book will look like this because of the tension that you have just exerted. Still on the table. The same way, if you exert this compressive force, compression, if you exert it on the material will be compressed. This is the new length, this is the new dimension, and this is the old dimension. So the material is compressed. So a tensile stress helps to elongate a material, but a compressive force, it compresses the material. Also, the shear, let's assume that the dotted line is still the original material, the book. The shear stress is a parallel force, is a parallel stress. let's assume it acts in this dimension, in this direction, then the body will be displaced in this manner. The body will be displaced in this manner, and as a result, there will be an opposite force here. So for it to move in this way, that means there is also an opposite force that moves in this direction. There are the theory of the books are still on the table. So in this case, this is a tension acting on the body. This is a compressive force acting on the body, and this is shear stress on the body. These are the three classes of stress. Now let us have something of this nature. Let us now suppose that a force F is being applied to the face of a rectangular table which has a cross-sectional area of A, and it looks like this. Now in this case, the force can be resolved into the normal and the tangential. Fn will be equal to F sine theta, while Ft will be equal to F cos theta. I got this sine theta by resolving F into this axis, and I got this cos theta by resolving F into this axis. This is under resolution of vectors. But the trick here is that the the angle where there is theta would take the cos, while the angle where there is no theta would take the sine. In this place, there is no sine, there is no theta, so it takes the sine. That's just the trick. In this place, there is theta, so it takes cos. But it is very, very good if you understand resolution of vectors. So you can check the video here. You can check this video. Alright, let's move on. There are two stress for that body. That is the normal stress, which is Fn, and the tangential stress, which is Ft. The normal stress can be compressive depending on what you want to achieve. And the second one is the tangential, which is also called the parallel stress or the shear stress. Okay, let's talk about strain. Whenever there is stress, there will always be an accompanied strain, which is defined as the relative change in the size or shape of a body due to the applied stress. Strain can also be defined as the fractional increase in the length of an object. Strain is dimensionless. Now, let us suppose that we have a body. A wire of length L. Let's call this L naught. If you elongate this body by exerting a tensile stress helps to elongate a material. If you elongate the body in this direction, then suppose that the new length that is formed is given as L1. It means that there is a change in the length. The change in the length can be referred to as L1 minus L0. Then the fractional increase in the length of that material is given as change in L all over the original length, which is L0. And this is the formula for strain. Let's assume that this is the symbol for strain. If the object is compressive, if it's a compressive force that you exert, like in the case of a balloon, If you put an empty bucket on that balloon, this, let's assume the length of this balloon is L1. The new length here is L2. The change in L is given as L2 minus L1. In this case, it will be negative. It is negative because it is compressive. The new length is less. The new length is less than the initial length. As a result, the extension in this case will be negative. Okay, I used L1 or L0, anyone, but it simply means the initial length. Alright, strain is dimensionless. It is dimensionless simply because the units will cancel out. The unit of change in length is meters. The unit of the original length is in meters, so they cancel out. Then strain becomes dimensionless or unitless. Alright, let us suppose that we have a body, a rectangular body, PQR. Suppose that we exert a shear stress on this rectangular block PQR, a shear stress in this direction. Then such tangential force in a unit cross-sectional area will give rise to the shear strain. This force causes points P and Q to be displaced through delta x and point P prime and Q prime respectively at the angular displacement theta. Let the change between Q prime and Q be equal to delta x. The shear strain will be given as delta x upon h. But note that delta x upon h is the same thing as tan theta, where theta is the angular displacement. But theta is always very small. The value of tan theta is always very small, that it can be approximated to delta x upon h. As a result, shear strain is equal to theta on a wire depends on which of the following. Stress is given as force over area. The force, assuming that we have a spiral spring, the force that is being exerted in a unit area, it can also be given as MA, and in some cases it can be given as mg. The reason is because of the case like this. In this case, the object, for instance, the 5 kg mass, upon placement on this spiral spring, it will exert its weight on the spiral spring. As a result, we are going to have a weight of 50 Newton if the acceleration due to gravity is given as 10 meter per second squared. It implies that F can be equal to mg, in this case acceleration due to gravity. It means that we can simply say that the stress really depends on the acceleration due to gravity, and it also depends on the mass of the load. Now, the area of a body, the area of the surface that the force is being exerted, can be given as pi r squared if it's a circular surface. We can consider the wire's diameter, because the wire's diameter will be included in the formula for area, since we have pi r squared, which is the same thing as pi d squared over 4. So it implies that we can have something of this nature, pi d squared over 4. but their relationship is inversely. The relationship here is directly proportional, but it depends on the three factors. It does not depend on the length of the wire. Another reason why it does not depend on the length of the wire is that the stress that is caused if the length of this wire is 5 meters. Suppose that I have another spiral spring whose length is 10 meters. If I exert the same amount of load on it, which is the 5 kg, it will bring about the same amount of force, and it will bring, as a result, bring about the same amount of stress in a unit area. Therefore, the stress on a wire does not depend on the wire's length. It depends on acceleration due to gravity. It depends on the diameter of the wire and the mass of the load. Thank you. Make sure you subscribe to this channel. If you have any question, put it in the comment section below. If you want me to deal with any topic, if you want me to produce a video regarding any topic, put it in the comment section below. Like, share with your friends.